Hello students, in today's lecture we'll study about the measurements. This is given as chapter number 2 section 2.3 to 2.5 of physics for class 11. The measurements discussed in today's lecture are measurement of length, measurement of mass and measurement of time. All the points discussed are very important. Please note down meticulously. Now let us study about the measurement of length. Measurement of large distances. Parallax is used to measure large distances such as distance between planets, stars, etc. What is parallax? Parallax is an apparent shift in position of an object with respect to another when we shift our eyes sideways. So we use this method to measure the large distances such as the distance between planets, stars, moons, etc. etc. Large distances. Please see the diagram 2.2 here. S is a planet in this figure. A and B are two observation points, 2 points of observation. The distance between them is small b. Angle ASB is equal to theta here is called the parallax angle or a parallatic angle. D is the distance. So as the planet is very far away, the distance B is very small as compared to capital D. That is, B is the distance between the observation points. B by D is very much less than 1. Therefore, theta is very small. Then we approximately take AB as the arc of length B of a circle with center as S. So we treat this as a arc of a circle with center S and distance D as the radius. So AS will be equal to BS. So this is approximately equal to D. So that AB is equal to B in this formula. AB is equal to B, that is equal to D theta, where theta is in radians. Therefore, D is equal to B by theta. To determine the size or angular diameter of a planet, if small d is the diameter of the planet and alpha is the angular size of the planet, the angle subtended by d at the earth, we have alpha is equal to small d by capital D. Having studied the measurement of large distances, let us study about estimation of very small distances, that is size of a molecule or and subatomic items. The size of molecule is very small, ranging 10 to the power of -8 meters to 10 to the power of -10 meters. A simple method for estimating the molecular size of oleic acid is described below. Oleic acid is a soapy liquid with large molecular size of the order of 10 to the power of -9 meters. We dissolve 1 centimeter cube of oleic acid in a alcohol to make a solution of 20 centimeter cube. Then we take 1 centimeter cube of this solution and dilute it to 20 centimeter cube using alcohol. That is, we make a solution with using alcohol. So the concentration of solution is equal to 1 over 20 into 20 centimeter cube of oleic acid per centimeter cube of solution. Next, we lightly sprinkle lycopodium powder on surface of water in a large trough, and we put 1 drop of this solution in water. The oleic acid drop spreads into a thin, very large and roughly circular film of molecular thickness on water surface. Then we quickly measure the diameter of thin film to get its area. Suppose we have dropped n drops in water. Initially, we determine the approximate volume of each drop, V centimeter cube. The volume of n drops is equal to n into V centimeter cube, and amount of oleic acid in this solution is equal to n into V into 1 by 20 into 20 centimeter cube. This solution of oleic acid spreads very fast on the surface of water and forms a very thin layer of thickness D. If this spreads to form a film of area A centimeter square, then the thickness of the film will be T. Thickness of film will be T is equal to volume of the film divided by area of the film. That is equal to NV divided by 20 into 20 into A centimeter. If we assume that film has no monomolecular thickness, then this becomes the size of diameter of a molecule of oleic acid. So estimation of small size is done using oleic acid in the laboratory. Range of lengths. The sizes of objects we come across in universe vary over a very wide range. These may vary from the size of the order of 10 to the power of minus 14 meters, that of a tiny nucleus of an atom, to the very large size of order of 10 to the power of plus 26 meter of the observable universe. We also use certain special length units for short and large lengths. These are 1 Fermi. 1 Fermi, that is written as 1 f, small f, that is equal to 10 to the power of minus 15 meters. 1 angstrom, that is 1 a to the power of 0, a hat 0 is equal to 10 to the power of minus 10 meters. 1 astronomical unit equals 1 AU. It is written as 1 AU. That is the average distance of Sun from the Earth. That is actually 1.496 into 10 to the power of 11 meters. This is the range astronomical unit. And we also express large distances in terms of a light year. 1 light year is equal to written as 1 LY, that is equal to 9.46 into 10 to the power of 15 meters. That is the distance traveled by light with a velocity of 3 into 10 to the power of 8 meters per second in 1 year. That is, light travels with a velocity of 3 into 10 to the power of 8 meters per second in 1 year. So large distances are expressed in terms of light years. 1 parsec. Sometimes we use parsec also. That is equal to 3.08 into 10 to the power of 16 meters. 1 parsec is the distance at which average radius of the Earth's orbit subtends an angle of 1 arc second. Table 2.3 shows the range and order of lengths which we come across in physics. So column 1 is the size of object or distance, and column 2 is length in meters. The smallest size, that is size of a proton, is 10 to the power of minus 15 meters. Then the next size is size of an atomic nucleus, which contains protons and neutrons. Its size is 10 to the power of minus 14. That is very small meters. Size of hydrogen atom is 10 to the power of minus 10 meters. Other lengths sizes are also given in this table. Please go through and note down. The largest distance or size of the object is that of a distance to the boundary of observable universe. So please note down, and it is also given in your textbook. The concept of measurements will be explained using few examples. Question number 1. Calculate the angle of part A 1 degree, part B 1 minute and part C 1 second in radians. That is, we have to convert 1 degree and 1 minute and 1 second into radians. It is given that use 360 degrees is equal to 2 pi radians. 1 degree is equal to 60 minutes and 1 minute is equal to 60 seconds. Answer. It is given 360 degrees is equal to 2 pi radians. Therefore, 1 minute will be equal to 2 pi by 360, or simplifying, pi by 180 radians. And we have to substitute the value of pi as 22 by 7 and calculate. So that comes out to 1.745 into 10 to the power of minus 2 radians. That answers part A. And part B, we will take 1 degree as 60 minutes. Therefore, 1 minute will be equal to 1.745 into 10 to the power of minus 2 radians divided by 60. This value we have taken from part A. That is 1 minute is equal to 1.745 into 10 to the power of minus 2 by 60 radians. Simplifying, we get 1 minute will be equal to 2.908 into 10 to the power of minus 4 radians. That is approximately equal to 2.91 into 10 to the power of minus 4 radians. Next part C. So it is also given 1 minute is equal to 60 seconds. Therefore, that 1 minute we have calculated as 2.908 into 10 to the power of minus 4 radians. That will be equal to, therefore, 1 second will be equal to 2.908 into 10 to the power of minus 4 radians by 60. That is the value of 1 second. Therefore, that is approximately 4.85 into 10 to the power of minus 6 radians. Question number 2. A man wishes to estimate the distance of a nearby tower from him. He stands at a point in front of the tower C and spots a very distant object O in line with AC. He then walks perpendicular to AC up to B, a distance of 100 meters, and looks at O and C again. Since O is very distant, the direction of the direction BO is practically the same as AO, but he finds the line of sight C shifted from the original line of sight by an angle theta is equal to 40 degrees. Theta is known as parallax that we have explained in the previous slide. Estimate the distance of tower C from his original position A. Please see the figure below, wherein the man stands at point A in front of tower C. This is a tower C. AC is a tower and he stands at position A in front of tower and spots a distant object O, in line with AC. So distant object is here in line with AC. He then walks perpendicular AC to AC up to B. So he wants perpendicular. This is 90 degrees, exactly perpendicular, and he stands at position B, which is at a distance of 100 meters, and looks at object O again. O and C again. So he from point B he looks at C as well as at O, distant object O. Since O is very distant, the direction BO is practically the same as AO. So BO and AO and BO are practically the same, but he finds the line of sight of C is shifted, but the angle C is shifted from the original line of sight by an angle theta. This theta is given as 40 degrees. That is parallax. Due to parallax, he shifts his angle. And we are required to calculate the distance of tower C from his original position. So we have to find the distance AC. That is AC. So let us work out. Given parallax angle is equal to theta, parallax angle theta is equal to 40 degrees. Therefore, AB is equal to, from the knowledge of our geometry, is AB is equal to AC tan theta. Therefore, AC is equal to AB by tan theta. That is, AC is given as AC is equal to 100. That is, AB is 100 meters divided by tan 40. Therefore, 100 meters by tan 40, we have to see from table, it is 0.8391. That is 119 meters. The answer is the distance AC is 119 meters. That is the answer. Example 2.3. The moon is observed from two diametrically opposite points A and B on Earth. The angle theta subtended at the moon by two directions of observation is 1 degree 54 minutes. Given the diameter of Earth to be 1.276 into 10 to the power of 7 meters, compute the distance of moon from the Earth. Answer. We have theta is given as 1 degree 54 minutes. That is equal to 114 minutes. Again, we have to convert it into seconds. 1 into 60 into 4.85 into 10 to the power of minus 6 radians. Because 1 second is equal to 4.85 into 10 to the power of minus 6 radians. That is equal to 3.2 into 10 to the power of minus 2 radians. Also, B is equal to AB is equal to, it is given, B is equal to 1.276 into 10 to the power of 7. We also know that D is equal to, that is the distance between moon and the earth, D is equal to B by theta. We know the value of B as 1.276 into 10 to the power of 7 divided by the angle theta 3.2 into 10 to the power of minus 2 meters. That is equal to 3.84 into 10 to the power of 8 meters. Next example. The sun's angular diameter is measured to be 1920 seconds. The distance d of the sun from the earth is 1.496 into 10 to the power of 11. What is the diameter of sun? Sun's angular diameter alpha is given as 1920 seconds. Therefore, that we have to convert seconds into radians by multiplying with a factor 4.85 into 10 to the power of minus 6 radians. That multiplying we get 9.31 into 10 to the power of minus 3 radians. Sun's diameter d is equal to alpha into capital D. Small d is equal to alpha into capital D. That is equal to alpha we have calculated is as 9.31 into 10 to the power of minus 3 radians into capital D. That is angular diameter is 1920 seconds. The distance d of sun from earth is 1.496 into 10 to the power of 11 meters. So answer is 1.39 into 10 to the power of 9 meters. Example 2.5. If the size of a nucleus in the range 10 to the power of minus 15 to 10 to the power of minus 14 meters is scaled up to a tip of sharp pin, what is roughly the size of an atom? Assume the tip of pin to be of the range 10 to the power of minus 5 to 10 to the power of minus 4 meters. The size of nucleus is in the range of 10 to the power of minus 15 meters and 10 to the power of minus 14 meters. The tip of the sharp pin is taken to be of the range of 10 to the power of minus 5 meters and 10 to the power of minus 4 meters. That is given in the problem. Thus, we are scaling up by a factor 10 to the power of 10. An atom roughly of size is of roughly of the size 10 to the power of minus 10 meters will be scaled up to a size of 1 meter. Thus, a nucleus is an atom is as small as size as the tip of a sharp pin placed at the center of a sphere of radius of about 1 meter long. Measurement of mass. Mass is a basic property of matter. It does not depend on the temperature, pressure, or location of the object in space. The SI unit of mass is kilogram. Symbol is kg. It is defined by taking the fixed numerical value of the Planck's constant h to be 6.62607015 into 10 to the power of minus 34 when expressed in unit of joules, which is equal to kg meter square per second, where the meter and seconds are defined in terms of c, that is velocity of light, and frequency of the cesium. While dealing with atoms and molecules, the kilogram is a convenient unit for kilogram is an inconvenient unit. In this case, there is an important standard unit called the Unified Atomic Mass Unit U, which has been established for expressing the mass of atoms as one unified atomic mass unit, 1U, that is equal to 1/12 of the mass of an isotope 12C6, that is equal to 1.66 into 10 to the power of minus 27 kg. Mass of commonly available objects can be determined by a common balance like, like the one used in a grocery shops. Every day we come across the balances used in grocery shops. Large masses in the universe like planets, stars, etc., based on Newton's law of gravitation, can be measured by using gravitational method. For measurement of small masses of atomic and subatomic particles, we make use of mass spectrograph in which the radius of the trajectory is proportional to the mass of a charged particle moving in an uniform electric magnetic field. Table 2.4 shows the range and order of masses. So column 1 shows the object and column 2 gives mass in kg. Electron. The mass of an electron is 10 to the power of minus 30 kg. The mass of proton is 10 to the power of minus 27 kg. Uranium atom weighs about 10 to the power of minus 25 kg. Similarly, so many other items are listed here. You please note down and go through it. The largest mass is that of an observable universe, that is 10 to the power of 55. So the range and order of masses vary from 10 to the power of minus 30 kg to 10 to the power of plus 55 kgs. Measurement of time. We use an atomic standard of time which is based on the periodic measurement periodic vibrations produced in a cesium atom. I read once again for you. We use an atomic standard of time which is based on a periodic vibrations produced in a cesium atom. This is the basis of the cesium clock, sometimes called atomic clock. So cesium clock is called atomic clock, which is used in national standards. In cesium atomic clock, the second is taken as a time needed for 9,192, 631, 770 vibrations of radiation corresponding to the transition between two hyperfine levels of ground state of cesium-133 atom. The vibrations of cesium atom regulate the rate of this cesium atomic clock just as the vibrations of a balanced wheel regulate on an ordinary wristwatch or the vibrations of a small quartz crystal regulate a quartz wristwatch. So the basic principle is same as the normal atomic clock, normal wristwatch or a quartz crystal clocks. And cesium atomic clock is known as the atomic standard clock. The accuracy of an efficient cesium atomic clock is of the order of plus or minus 1 into 10 to the power of minus 13, that is 1 part in 10 to the power of 13, that is the stability of the atomic clock. Table 2.5 shows the range and order of the time interval. So events are given in the column 1 and the time interval is in seconds is given in column number 2. So some of the events are lifespan of a most unstable particle. That is, the unstable particle's lifespan is 10 to the power of minus 24 seconds. You can imagine normal second itself is very small, whereas the lifespan of an unstable particle is 10 to the power of minus 24 seconds. Then time required for light to cross a nuclear distance is 10 to the power of minus 22 seconds. Period of X-rays is 10 to the power of minus 19 seconds. So like this, different events are listed here in the column 1. Please go through and note down in your notebooks and remember some of them. And most importantly, the largest ranges are the age of universe is 10 to the power of 17 seconds. Similarly, time since Dyson became extinct is 10 to the power of plus 15 seconds. Age of Egyptian pyramids is 10 to the power of 11 seconds and so on. You please go through and remember the range. With this, we come to the conclusion of measurement part of chapter number 2. In the next lecture, we will study accuracy, significant figures, and dimensions of physical quantities. Till then, goodbye.